Okay, so this is our lesson on scientific notation. I'm going to begin just by playing this little presentation because I think it really helps demonstrate what is happening. I'll just walk through it. I think there is probably some sort of sound associated with it, but we don't need to listen to it. We'll just go at it at our own pace. The need for other notation. So real world applications of math frequently require the use of very large numbers or very small numbers. This is especially true in science. Some examples, if you count all the number of cells in the human body, you end up with this massive number. And in order for us to write this number every single time, it would take a lot of effort, right? We'd have to remember how many zeros and all that stuff. So there is a notation that we're going to learn to help us make that a little faster. Another example is the number of neuronal connections in the human brain is approximately that number there. I'm not even going to try to guess what it is. The estimated number of atoms in the observable universe is that number over there. You can actually go the other way as well. We don't have to have very large numbers. In science, I don't know if you guys have gotten to chemistry where you learn about electrons, protons, and neutrons, or physics, but there is something in our atoms that exists that is called an electron, and it is a very, 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 very tiny subatomic particle. And the weight, the mass or the weight of that is that many grams. So again, to sit there and count the number of zeros and write that every single time would be very cumbersome. And so we learn another notation. Large numbers. One way to easily display and work with awkwardly large numbers is to use scientific notation. As you'll soon see, scientific notation is based on multiplication by powers of 10. So 10, 10 squared, 10 to the power of 3. To get an idea of how scientific notation works, let's do a quick investigation. So we're actually going to come back to this because right now we haven't really learned how to do scientific notation. So let's first learn and see if we can actually match these. Okay, so let's go to our worksheet, and in this worksheet, it says scientific notation, a handy way to write really, really small and really, really big numbers. Now, if we were to break down scientific notation, this is what we would find. Hold on, let me just pause this. So if we were to take a look at the example that we have on the screen, it's 6.02 times 10 to the power of 24. If we were to break down this example, here are a couple of key features. The first is you have to recognize that this number that we're going to write is always going to be between the numbers 1 and 10. So if you have a number in scientific notation that is more than 1 and 10, then it's not in proper scientific notation. It can have decimals. It doesn't have to be a whole number, but it has to be between 1 and 10. You're always going to have a multiplication sign. And then like the little PowerPoint slide thing suggested, all of our scientific notation is going to be in base 10. That means we're going to have 10 to the power of something. And in this example, we have 10 to the power of 24. But this number doesn't have to be positive. It can be a whole number that is positive, or it can be a whole number that is negative. Let's look at two examples here. We have 2.8 times 10 to the power of 5 and 2.8 times 10 to the power of negative 5. Now, if we were to write this in expanded form, because we're doing our powers unit right now, we're used to writing things in expanded form, it would basically be 2.8 times 10 times 10 times 10 times 10 times 10, which would give us 280,000. The other example, if you are writing 2.8 times 10 to the power of negative 5, really 10 to the power of negative 5 is like saying 1 over 10 to the power of 5. So this time you're dividing by 10. So it's 2.8 divided by 10, divided by 10, divided by 10, divided by 10, and so on. And the answer you get is 0.000, I don't know how many zeros I just said, 28. Okay. However, there has to be an easier example than writing out all those tens and multiplying, etc. And I'm going to show you that right now with those two examples. So let's look at 2.8 times 10 to the power of 5. In order for us to solve this, what we're going to do is we're going to start with the number 2.8. And in scientific notation, the decimal place is super important. When the number is a whole positive number, it means you are going to be moving to the right. And that's because we want our number to get bigger. In order for our number to get bigger, you move the decimal place to the right. So what you do is you start with 2.8 in the decimal place there, and you're going to move it over 5 units to the right. So 1, 2, 3, 4, 5. And then at the 5th place is your new decimal point. And all you're going to do is you're going to put in a 0 in all these little, I guess, U's or these little holes that I've made. You just add in a 0. So your final answer is going to be 280,000. The 0 after the decimal place is not important. You can just drop it. That's your final answer. And we do this for every single question with scientific notation. There are a couple of exceptions. So when we're doing the examples, I will show you a couple of cases where it doesn't work. How about the other example? We have 2.8 times 10 to the power of -5. In this example, when the exponent is a negative, you are going to be moving the decimal place to the left because we want our number to become smaller and smaller and smaller. So again, you start with 2.8 because that's what the question gave you. And then you're going to move this decimal place 1, 2, 3, 4, 5 units to the left. And you're going to fill in the rest of the spaces with zeros. In this case, the 0 is important before the decimal place because it's kind of awkward to write it as 0.000028. Often when a number, it's not wrong, you could write it like that, but often you're going to see that 0 before the decimal place. Can a number have 2 decimal places? No, it can't. So make sure your numbers always just have 1 decimal place. Questions? Okay, another thing I want to tell you is these numbers right here are known as, it's known as scientific notation. And these numbers over here are in standard form. So you're going to see us use the words a lot, go from standard to scientific or scientific to standard. And that's what we're going to practice to do. And let's get it. All right, question number 1. We have 3 times 10 to the power of 5. Do you notice in this question there is no decimal place? I mean, there's no decimal place written. What that means is this question actually looks like this, 3.0 times 10 to the power of 5. So when there's no decimal place written, you just have to add a decimal place on the right-hand side of the number, and then you do exactly what we did earlier. So we're going to have 1, 2, 3, 4, 5, add in your zeros, and then I always like to write it properly. So this answer would be 300,000. Indeed. Okay, and for all these questions, we're going from scientific notation to standard notation. We're not going to do every single one of them because it will be repetitive. Let's go ahead and try question number 4. Question number 4 is interesting. 7.295 times 10 to the power of 0. This is actually important for your quiz. Anything to the power of 0 is equal to. So this question is basically saying 7.295 times 1, which is going to be itself. And your final answer is just going to be 7.295. What about if you have a negative number to begin with? It doesn't matter. Negative 2.68895 times 10 to the power of 1. What we're going to do is we're going to, I'll just rewrite the number, negative 2.68895. We're going to move our decimal place 1 unit to the right or to the left? To the right. And so our answer is going to be negative 26.8895. Make sense? Okay, let's try some negative exponents. So let's try question 7, 4.466 times 10 to the power of -2. So we begin with 4.466. 10 to the power of -2 means I'm actually moving the decimal place now to the left. So we're going to start over here. We're going to go 1, 2 units, and we're going to fill in the spot with a 0. So our final answer is just going to be 0.04466. Right, because we moved it over 2 decimal places. How about this question here? Question 8, 4 times 10 to the power of -4. Again, there's no decimal place, which means it's just going to be a 4.0. You're going to take that and move that 4 times over to the left. 1, 2, 3, 4. And then we have 3 zeros before it. So our final answer is going to be 0.00040. You guys, when something is to the power of -0, does that matter? No, it doesn't, because really this is like saying 1 times 10 to the power of 0, which is just 1 over 1, which is 1 anyways. So don't get confused by this question. The answer for this one would just be -2 times 1, which is -2. Emma? You don't have to put the last 0. Emma? What's happening with you guys? So confusing. All right, let's try. That's it. That's all we're going to do. Let's do maybe 6 more examples going the other way. So in these examples, we're going from standard notation to scientific notation. I want to do a couple more of these because I find that these are a little bit more tricky than the other ones. So 50,000. We're trying to convert this to scientific notation. Where you have to ask yourself, where is the decimal place in this question? And the answer is it's going to be right after the number. Now remember, you have to try to move the decimal place over so that you're left with just a number between 1 and 10. So when I do that, it's going to be 1, 2, 3, 4. And I moved my decimal place to the left. So that means I'm making my number smaller. So what do you think my exponent is going to be? Is it going to be positive or negative? Yeah, good. And so my final answer here is going to be 5.0 times 10 to the power of 4. And I actually have to correct what you just said. So hold on. Okay, let's try question number 3, 839.18. So I'm going to write that here, 839.18. So again, to make it into scientific notation, I need to move the decimal place over so that it's between the first 2 digits. And I'll be left with 8.3918 times, what do you think the next part will be? 10 to the power of 2, exactly. Because when you expand 8.3918 times 10 to the power of 2, you'll get a bigger number. We'll do one more over here. Let's try question number 5. Negative 1,280.087. I'm going to move the decimal place over 1, 2, 3 units that way. And so I'm going to be left with negative 1.280087 times 10 to the power of 3. Yep. Okay, what about if we're going in the other direction? So in this example for question 7, 0.087. So to make 0.087 into a scientific notation, we're moving the decimal place over twice. And we're going to be left with 8.7 times 10 to the power of -2. So when you're going from standard form to scientific notation and you're moving your decimal place to the right, you end up with a negative exponent. I think you guys are getting the hang of it. So let's do one last one. I like number 9 because it seems really complicated. So what we're going to do is, I guess I'll write it just up here. 0.00040000281. We're going to move this over 1, 2, 3, 4 times. And we're going to be left with 4.0000281 times 10 to the power of -4. Good job. Okay, I think that's enough examples. So your homework, you're not going to get to do it now because we're going to start our quiz, but your homework is going to be all of handout G. And there are solutions at the bottom. So if you do this, you'll be really prepared for the assignment we're going to do in tomorrow's class. Assignment.